Hello, here is our third lecture, our solar system, the terrestrial planets. Let's take a look at our learning outcomes here. We want to be able to list the planets in their correct order from the sun, understand the relationship between mass and gravity, describe the primary planetary objects found in our solar system, their compositions and physical characteristics, identify and interpret surface features of planets and moons, and briefly describe how the solar system formed. So a quick overview of our solar system. Our solar system formed 4.6 billion years ago from a nebula. And we took a look at a photograph of a nebula from the NASA site, I believe is where that came from, that I showed you in the previous lecture. Let me jump over here. These images are from the Hubble site. And you may or may not know what the Hubble is, but it's a telescope that is orbiting the Earth. It was launched using the space shuttle some years back and has been in service ever since. And it takes the best images of space. So this part of the site has photographs of nebula, including the one that I used for our previous lecture, which is this guy here. Let's take a look at some of the others here. And again, these nebula are collections of dust and gas, which over time begin to condense. Matter coalesces, clumping together, becoming larger and larger. And where the greatest concentration of matter is, if you accumulate enough, gravitational attractions get high enough, things get hot enough, and you can create a star. And then from the leftover material, you may form planets and even moons around those planets. So I encourage you to come to this website and just click around. There's a lot of great images on here that I think you might enjoy looking at. Let's go back to the lecture. So the nebular theory and formation of our solar system. We got into this, and I think the smart figure tutorial from your textbook is quite good. This link here will take you to an excellent summary of the formation of our solar system. But for the sake of being brief, I won't click on it now, but I would encourage you to do so yourself. And then this is from your textbook. This is more or less the same as what was included in the previous lecture. Our solar system is found within a galaxy that is about 6 billion years old, called the Milky Way galaxy. And the Milky Way galaxy is contained or found within a universe that is 13.8 billion years old, or was formed 13.8 billion years ago. The universe was created through the process that we call the Big Bang, and everything that we know of began at that time. Contained within our solar system are 8 planets, at least 190 moons, 800,000 asteroids, 3,500 comets, meteoroids, and dwarf planets. And of course, all this material is orbiting the sun due to the sun's gravity. And as we have mentioned before, the sun is huge and contains almost all the mass in our solar system. But our sun in the grand scheme of things, is insignificant. It is one of only 100 billion or more stars in our galaxy. The Milky Way is vast, containing billions and billions of stars. And the gravity from that sun is keeping all the planets and other stuff in orbit around it. Our sun is technically classified as a yellow dwarf star, but it's pretty average as far as stars go. This video here is kind of fun to look at because it puts the size of our sun in context with other stars. And you might recall from that previous lecture how big our sun is relative to the size of the planets.
The sun is 93 million miles away, and that means in actuality it's immense. You could fit 1 million Earths inside the sun.
It's over 1 million kilometers in diameter, yet our sun is tiny compared to the really big stars out there. Eta Carinae, over 5 million times larger than our sun. Betelgeuse, 300 times larger than Eta Carinae. If it was our sun, it would reach as far out as Jupiter. And then there's this monster, VY Canis Majoris, the largest star ever discovered, 1 billion times bigger than our sun.
An arm of the Milky Way as seen from Earth. So the Milky Way galaxy is classified as a spiral galaxy. You could think of it being the shape of a dinner plate with like a golf ball or tennis ball right in the middle. If you are lucky enough to get to a place that's dark enough, you may be able to see the Milky Way, such as is shown here in this photograph, looking side on, so looking at the side of the dinner plate. And these are some of the hundreds of billions of stars in the Milky Way that you can see here. So as a review, we have the sun at the center of our galaxy, at the center of our solar system, excuse me. Then we've got Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, Saturn. This would be the orbital path of Uranus, and then Neptune. And you see that everything is more or less lined up on the same level or same plane, which we call the orbital plane or plane of the ecliptic for the planets. And this image below shows the planets and sun at their relative sizes to one another. The sun being by far the most massive. And of the planets, the Jupiter is the most massive. This also shows the spacing of the planets. Of course, they are not this close to one another, but we see the terrestrial planets grouped together, and then the much further spacing between the gas giant planets. So a quick overview of the solar system here. The planets, internal structures and atmospheres. We have two types of planets based on location, size, and density. Terrestrial are the Earth-like planets. Terrestrial comes from the word terra, or earth. And then the Jovian planets are those that are like Jupiter, Jovian being another word for Jupiter. The terrestrial planets include Venus, Mercury, Venus, Earth and Mars. They are relatively small, dense, and rocky. They have relatively large cores of iron and nickel, thin atmospheres of carbon or nitrogen, and they have shorter revolutions around the sun, or shorter years around the sun, because they are all pretty close to the sun, so it doesn't take them that long to make one trip around it. Jovian planets include Jupiter, Saturn, Uranus, and Neptune. These are all relatively large, low in density, and mostly made of gas. Okay, they're massive compared to the terrestrial planets, with thick atmospheres of mostly hydrogen, helium, methane, and ammonia. And their years are longer because they're further from the sun and therefore have longer path to travel one time around it. This illustration shows the structure of the planets. We looked at Earth already with its core, mantle, and crust. We see that all the terrestrial planets, Mars, Earth, Venus, and Mercury, have relatively large cores relative to the overall size of the planet in comparison to the Jovian planets whose cores are significantly smaller relative to their overall size. On the other hand, they have very thick atmospheres. These are the visible clouds from Jupiter, Saturn, Uranus, and Neptune. Beneath that is the hydrogen and helium. It's the gray layer. And then when you get deep enough into Jupiter and Saturn, the hydrogen becomes liquid. So you basically have a vast ocean of hydrogen. For Uranus and Neptune, they're so cold, so they instead have ice. And then eventually you get down to a rocky iron core. A brief summary of the terrestrial planets from nearest to farthest from the sun. So we start here with Mercury, just a bit larger than our moon. It has a moon-like surface, heavily cratered, as you can see in the photograph of it there, with some areas that are smoothed out, and essentially no atmosphere. So for Mercury, not much has changed for a long, long time. Because there's no atmosphere, there are no atmospheric processes. There's no weather. Of course, there's no water. So there's nothing flowing or blowing over the surface to change anything. It's also a geologically dead planet. So there's no internal processes that are going to affect the surface, such as lava flows, which would come from magma from beneath. So the surface of Mercury has looked very much the same for probably billions of years. So it's a very old surface. Mercury rotates or spins on its axis very slowly. In fact, it takes 176 Earth days for it to make one rotation. Because it's closest to the sun and has the shortest year, equivalent to what would be 88 Earth days. Mercury has the most extreme temperatures of any planet. It is very close to the sun, so not surprisingly, it gets very hot, up to 800 degrees Fahrenheit. What may be surprising is that it gets extraordinarily cold there as well, negative 290 degrees Fahrenheit. And this is because of this very slow rotation. You end up with these extraordinarily long nights. The side of the planet that is turned away or spun away from the sun stays in darkness for what would be 88 days. And without an atmosphere, there's nothing to trap the heat, so all the heat escapes into space and it becomes extraordinarily cold. Venus. Only the moon is brighter in the night sky. Venus can be seen commonly at night. It'll be the first star that's out. It will shine before the sky is even dark and you can see any other stars. It's similar to Earth in size, density, and relative position to the sun. It has a very dense atmosphere, which is mostly carbon dioxide. So in that way, it's definitely different than Earth. If it has a thick atmosphere of mostly carbon dioxide, how would that affect the temperature on Venus? Well, if you know anything about global warming, you know that that is caused by greenhouse gases. And the greenhouse gas that we are most concerned with here on Earth is carbon dioxide, because it is an effective trapper of heat. So Venus's atmosphere being almost all carbon dioxide, you can imagine a lot of heat is trapped. The result is Venus is the hottest planet, even though it's second closest, to the sun. It's also orange. If you were to be able to get to the surface, everything would appear orange. And this is because the atmosphere is so thick that all the other wavelengths of light are filtered out. But you wouldn't be able to survive on the surface. It's not only extraordinarily hot, but the atmospheric pressure would be comparable to being a mile underwater, and you'd be crushed under the weight of the air. More on Venus. So with Venus's surface, we can't see it, but it has been mapped by radar. And some features that are noteworthy are very widespread lava flows. We see that lava flows much further. It spreads out, covering huge areas of Venus's surface. And this is because it's so hot that it takes the lava a very long time to cool down to the point of solidifying. There are some large impact craters on the surface of Venus. It's noteworthy that there are no small ones. The reason for this being that Venus's very thick atmosphere causes any smaller meteorites to burn up on their way into and through the atmosphere. So only the biggest meteorites make an impact on the surface. The surface is littered with many extinct volcanoes. It does not seem that they are active any longer. Earth, a much more pleasant sight. Earth is unique in important ways. It's the only planet with liquid water. At least I should say liquid water on its surface. It has a thin atmosphere that keeps the surface from not getting too hot or too cold. It's kind of just right. Traps enough heat that it can sustain life as we know it, but doesn't trap too much heat. The atmosphere also allows for weather. And from the weather, of course, we get rain, and from rain we get streams, and weather gives us wind. So we have these superficial processes acting on the Earth's surface, causing it to constantly change. Earth is also tectonically active, which is relatively rare in our solar system. Tectonic activity drives the building of mountains and volcanoes. And with this, you are also constantly changing the Earth's surface. So in contrast to Mercury's surface, which is littered with craters, Earth has very few craters. Not because Earth hasn't been impacted by meteorites, but the meteorite impacts have been erased by the tectonic activity and their surface processes, such as stream and wind erosion. Let's talk about our moon. It is very large relative to the size of the planet that it orbits. It's the fifth largest altogether in the solar system. But even the largest moon is much, much smaller than the planet it orbits, that being Jupiter. So why is this the case that our moon is as big as it is relative to the size of Earth? Well, it is unique in that it is not a captured dwarf planet or asteroid, which is the origin for almost all the other moons. Instead, our moon was formed in a most unique way. Very early on in our solar system's formation, Earth and another planet collided. This planet blasted into the Earth, kicking out part of the semi-solid Earth into space, and part of the planet impacted it. But this debris did not get launched so far that it could escape Earth's gravity. And instead, the material began to orbit the Earth, coalesce, and over time, all that material accumulated into a single single mass, which is today the moon. Let's take a look at this video summary of forming the moon. So very early on in our solar system's formation, you would have had all the planets and all the moons looking something like this in this semi-molten state, extraordinarily hot. All right, let's talk about the moon a little more here. It is 1/6 as massive as Earth, so therefore it has about 1/6 the gravity of Earth. In other words, you would weigh 1/6 of what you weigh here on Earth if you were to go to the moon. We only see one side from Earth. Why is this? I don't know if you've ever done this, but if you were to observe the moon over the course of, say, a week, you would notice that you are always looking at the same features. They never change. You could look at the moon at any time, whether it be over the course of a week, over the course of a month, over the course of years, and you're always going to see the same things. And this is because the spin of the moon, on its axis, as it's orbiting the Earth, is happening at the same rate. So one spin of the moon is locked in with its spin or orbit around the Earth. So as it is orbiting the Earth, it is turning on its own axis at exactly the same rate. And the result is that we always see the same side. The other side that we don't see is referred to the dark side of the moon. You perhaps have heard that term before. Some of the surface features have been studied extensively. As you might imagine, the moon is pretty close and we can see it pretty easily. I mean, if you have just a good pair of binoculars, you'll be able to see some of these features yourself. And through observations and discussions and testing, we have come up with a history for the moon evolving in 4 distinct phases. The first phase created what we call the highlands area. And in the image here on the left, these are the lighter colored areas that you see cratered. These would have been the first areas that formed just after the moon had cooled down enough to form its crust. So these highland areas are the result of the solidification of silica-rich magma. Silica-rich magma will be light in color, hence the light gray color that you see there. From about 4.4 to about 1 billion years, the moon, just like every other planetary body and every other moon in our solar system, was heavily cratered. There was a lot of stuff out there as all this material was continuing to coalesce into other planetary bodies. So the smaller stuff was being added to the larger stuff. From 3.8 to about 1 billion years ago, the moon experienced volcanic eruptions where basaltic lava flowed across the surface and filled in some of the low spots, creating these smooth, dark surfaces that we call the maria. Maria is another word for sea. And so these look a little bit like oceans relative to the higher and lighter in color landscape. The difference in color is because this is a different type of rock. It is not silica rich, but instead more rich in iron and magnesium. And this is a rock very common on Earth called basalt. And basalt comes from lava flows, just as it did on the moon. And then the last stage would have been the formation of what are called rayed craters, and that happened in the last 1 billion years. Let's take another video tour here. Let me get you over to that screen. And again, this would have been the case for all planets and all moons during this period of time. Heavy bombardment from meteors. So many meteorite impacts, creating what we call impact basins. Planets that have geologic activity and atmospheres, like the Earth, are able to erase those craters because the crust is constantly being renewed. The Moon, like Mercury, has been geologically dead for a long time and has no atmosphere. So the planet has not been able to repair or erase the cratering, and so we still see the craters today. So the moon's surface, like Mercury's, very old surface, versus the Earth, which has a very young surface. And here this illustration summarizes what I just mentioned, the forming of an impact basin by a meteorite. In your book, there are a lot of illustrations. And the phrase, "a picture is worth 1,000 words," is very relevant in the earth sciences, which are a very visual area of study. So as you are doing your reading or perusing your textbook, scrolling through it on your phone, or you're looking at it on your computer, or whatever you're going to be doing, I would really encourage you to take a look at the pictures, because a good, careful study of the picture and reading and thinking about the captions will teach you a lot. And in some cases, if you don't have enough time to complete the reading, just looking at the images themselves will provide you with a lot of information. So at the very least, do that as you go through the chapters. Mars. Mars is considerably smaller than Earth at only half of Earth's diameter. Its year is nearly twice as long as Earth's, though. As you might imagine, it is further from the sun, and therefore it takes a longer time to revolve around the sun. It has that distinct red color with ice caps. And a thin atmosphere. Its atmosphere is only 1% the concentration of Earth's, and is mostly carbon dioxide. Its surface temperatures range from 220 degrees below 0 Fahrenheit to as much as 70 degrees Fahrenheit. But still, with the exception of brief periods of time when it would get up to 70, it is too cold for us to be there without proper equipment and housing. I say that because, as you may know, we plan to visit and colonize Mars here in the upcoming years. That is going to happen in your lifetime. NASA Mars pictures. Get us over to that screen. So the Hubble site is excellent, as is the NASA solar system site. There's all kinds of good stuff on here. So if you find this astronomy stuff interesting, I would encourage you to come over to these sites and click around and just have some fun looking at different stuff. This is Mars with its red color. It has ice caps at the pole. Let's see here. Let me get this correct. Yeah, so this is the North Pole there with the ice cap. Mars also has the largest volcano in the solar system, Olympus Mons. I'm going to talk about that in just a moment. Why don't I go back to the lecture and I'll do that now. So the southern hemisphere of Mars is heavily cratered, similar to the Moon and Mercury. This is the oldest surface of the planet, hence the heavy cratering. In contrast, the northern hemisphere is extraordinarily smooth. In fact, it is considered to be perhaps the smoothest surface in the solar system. And this happened by extensive lava flows. Around the equatorial region of Mars, there's an area called the Tharus Bulge, and associated with that are some very interesting features. The largest volcanoes in the solar system, including Olympus Mons. We see this photograph here of Olympus Mons with the state of Arizona superimposed on top of it. And you see that Olympus Mons is actually larger than the state of Arizona. Mount Everest is the tallest mountain on Earth. Olympus Mons is more than twice as tall as Mount Everest. This region also contains the longest and deepest canyon in the solar system, called Valles Marineris. It would extend from the west to the east coast of North America and is twice as deep as the Grand Canyon. Mars has 2 small moons, which are probably captured asteroids. One thing that is exciting about Mars for us is that it had liquid water in its ancient past. Based on careful studies of Mars, many astronomers believe that it could have looked like this image over here on the left in its ancient past. When I say ancient past, going back, let's say, 1 billion or more years ago. It could have actually had seas of water. We see evidence for stream valleys, meaning that liquid water would have flowed over its surface. We find rounded rocks, and the way that we round rocks on Earth is when they are carried in water, either in a stream or by waves on the beach. So it would stand to reason that they became rounded for the same reasons on Mars. We also find that there is ice beneath the surface, just a few feet down. And in fact, it seems like this ice may melt at certain times in the year and form what are called the Linnae, which is what this image is showing us here on the right. We see these seasonal, what look like streams happening on the surface. And it may be that the ice melts in the subsurface, again, maybe just a few feet down, and causes these features to appear on the surface. More study is needed. So to end this lecture, I have another mini quiz here. 10 questions. You'll answer these questions in Canvas under the assignment Mini Quiz 2. And again, these will help you to review what was covered in this lecture and prepare you for the module ending quiz. So I'll end this lecture now. So, bye-bye.